So let me introduce our speaker today. So we have Sascha Hilgenfeldt from the University of Illinois Urbana-Champaign, and he's going to tell us about, I think, topological defects and curved surfaces, a subject that I did in my PhD days. So I'm very, very interested to hear about that. So Sascha, we'll have a 40-minute talk, then 20 minutes for questions and answers, and then just a 20-minute free-for-all at the end, which is generally proved to be very, very successful in the past. So yeah, over to you, Sascha.
Very good. Thank you, Adil. Thank you so much for the opportunity to talk. I'm sharing my screen, and I hope it's visible now in full screen. Yeah, so I'll talk about placement and symmetry of singularities on curved surfaces today. And what I want you to take away from this is that there are simple criteria that you can use to predict when and how curved crystals, that is arrangements of identical units that form a lattice and are forced to conform to a curved surface, when and how that such curved crystals must be irregular, or when they can still be completely regular. Much of this work, almost all of the work that I'll be talking about on the theory side, was done together with my graduate student Siddhansh Agarwal, who really did a marvelous job here and really did basically all the work here. And I will give credit to other collaborators as I go along. I'll motivate what we've been doing largely by systems from biology, but also some from engineering science. And we'll focus there on the onset of disorder. When do systems lose crystalline order? And we'll boil everything down to an elementary problem that will turn out to be not so elementary. There will be a lot of non-trivial results, even for the kind of the simplest problem that you can think of, namely the onset of disorder on caps of rotational symmetry. And by onset of disorder, I mean the occurrence of the first disclination. We will derive a new analytical criterion that, as far as we can see, is universally valid for that onset of disclination disorder. And in the last part of the talk, I will talk about the character of that onset, whether it's occurring as a continuous transition or discontinuous transition, and therefore, if the pattern of disorder is symmetry breaking or symmetry preserving. I'll say a few words about what I'm also interested in and what I'm working on a lot in these past years. Also motivated by biological domain systems, or generally domain systems of soft matter, space-filling arrangements of domains that you can interpret as bubbles in the case of foams, or cells in the case of either animal or plant tissues. And everything I'll talk about today will happen in two dimensions, will happen on a surface that will generally be curved, but what I'm showing you here are essentially flat arrangements of polygonal cells or bubbles that are obviously disordered. They don't have a particular long-range order that you can identify. And in these cases, we have been interested in inferring mechanical properties of these arrangements of domains just from the visual information. We found a couple of different ways of doing that, using geometric information like the length of edges in these, or the number of neighbors of the individual cells, of the individual domains, which I will throughout this talk try to color code consistently. That's not what I'm going to talk about today. I'm not going to talk about fully disordered systems. I'm going to talk about ordered systems, and the original motivation came from work that is still ongoing together with Richard Carthew's group at Northwestern, who is a developmental biologist who's working on Drosophila, the fruit fly that you all know is the workhorse of genetic biology. And the eye of the fruit fly, and famously of many arthropods, are faceted. And a wild-type fruit fly eye is very, very regular. If you take a cross-section parallel to the surface of the eye, you see this beautiful hexagonal pattern of these so-called ommatidia, the individual facet eyes. And within each eye, you have stereotyped patterns of cells that we're not going to talk about today. I will first point out another thing that I'm not going to talk about today. I'm not going to talk about the onset of disorder by polydispersity. That's something that we investigated a few years ago in looking at Drosophila pupil retinas. So this is during pupation, one eye of a Drosophila fruit fly that, again, as a wild type is completely regular. Every facet in this eye has 6 neighbors, and therefore everybody here is gray in color. But there are certain mutations in the pathway of planar cell polarity in the development of the fruit fly that lead to defects, that lead to topological defects that are indicated here as colors. The yellow guys have 5 neighbors, the blue guys have 7 neighbors, and so on. And we found that this can be fully explained by recognizing that the mutation leads to a variability or a greater variability of the cross-sectional area of the individual facets. So the idea here is, if you want to look at this theoretically, that you take this honeycomb pattern, this regular hexagonal pattern, and I will often flip back and forth in this talk between this cellular arrangement and its dual, which is this triangulated pattern of nodes that are located at the centers of the hexagons and have a hexagonal coordination with each other. So here's a regular triangulation of the plane. And what we did to explore polydispersity was to take the nodes and randomly displace them with a characteristic distance alpha. And as you can imagine, as you increase alpha, and then you reconstruct the Voronoi cells around the displaced nodes to again have a cellular pattern, you will first induce polydispersity of the size of the Voronoi tiles. And then if alpha is large enough, you will induce defects in the sense that not everybody is going to have 6 neighbors anymore. And here's just an illustration of how this works as you increase alpha. And it's indeed a threshold phenomenon. You can show that as you increase the polydispersity, here quantified as the coefficient of variation of area, the disorder, the coefficient of variation of neighbor numbers, stays 0 for a while. And then there's a critical onset above which you start getting defects in your structure. I'm just pointing this out, that this is a very obvious geometric way of understanding the occurrence of defects if you have polydispersity in your system, if your constituent domains are non-uniform in a certain way. But we're going to disregard that today in this talk. Today we're going to talk about monodispersed lattices. The units that are interacting are identical. There's no a priori reason to have polydispersity or defects. That would be an appropriate description of this pupil wild-type retina that I showed you. But you may also already have misgivings about maintaining this perfect order as soon as you introduce curvature. What you see on the right is a confocal image of an adult Drosophila eye that we took. And as you can appreciate, as the eye matures, it attains curvature, and in particular, it attains intrinsic curvature, Gaussian curvature. There are many such examples in biology and beyond, not just in many arthropod eyes, these beautiful facet arrangements on curved surfaces that make a lot of sense because insects have to have a large angle of view. And at the same time, the processing of visual information is surprisingly regular in the sense that that photon receptors that lie below these individual facets are connected to receptors in the neighboring facets in a very stereotyped way. And they need a regular array for the visual processing of information to work properly in the arthropod's brain, basically. Similar considerations apply to microlens arrays. Here's an illustration of microlenses fabricated in Al Crosby's group that are gleaning their principle from arthropod eyes, and they also want a certain angle of view while being a regular six-fold coordinated array of lenses. What you see on the right here is a structure on the membrane surface of an archaeal bacterium. The S layer, that is the membrane, is a regular array of lipids, basically. And you will maybe not quite see in this picture that there are defects occurring in certain stereotyped positions on those layers. Very relevant at the moment is thinking about defects on virus capsids. Virus capsids can have all sorts of shapes, as you may know. Very prominent examples here, SARS, HIV. In order to be a closed surface that is made of stereotyped protein units, there have to be defects in the unit. You can already see some of these indicated in red here. And it would be very valuable for us to understand when these defects occur, where they will be located. So what do we talk about when we say defects? Here are sort of the elementary defects, the elementary representatives of disorder in crystal lattices. Disclinations are simply lattice sites that have the wrong coordination number. A negative disclination here has more than 6 connections to neighbors. A positive disclination has fewer than 6. And if a positive and a negative disclination come into an adjacent position, they make what is known as a dislocation. And while the naked disclinations are defects of orientation, there is an angular defect associated with every disclination. When opposite sign disclinations come together and make a dislocation, the net effect is a defect of translation quantified by the Wellman-Burgers vector. Now you all know, and you knew that I was going to say that, there's Euler's theorem on any lattice, on any domain system. And you can apply it to this particular case of triangulated lattices. And it will tell you that you need a net topological charge that depends on the Euler characteristic of the surface of the system that you're looking at. So there's a net topological charge of 6 times the Euler characteristic that you need. And the topological charge of an individual defect is simply the mismatch between the average number of neighbors, which in triangulations must be 6, and the coordination number at the defect. So if you have a positive disclination that has 5 neighbors, it carries a charge of +1. And you all know the example of this object that for this audience I will call a football, that it cannot be tiled entirely by hexagons. It has to have, well, it has to have a total defect charge of 12 because its Euler characteristic is 2. And the easiest way of realizing that is to have 12 pentagons on its surface. But this is a closed surface. The most relevant case that we want to understand is the case of open surfaces with a boundary. Quite obviously for these examples of eyes and microlens arrays, but also if we're thinking about virus capsids, because they don't spontaneously emerge as closed surfaces, they have to assemble. And they often assemble en masse. So there are patches of these crystalline units growing on what is a template. And the template can be made, be constituted by various entities, but in many cases, for instance, it is the RNA of the virus. So this weird looking capsid shape of the HIV virus that I showed you a couple of times already is the nucleocapsid that surrounds the RNA, and its weird shape is templated by the underlying RNA coil. And you can see in both of these simulations here, in both of these illustrations, that there are very stereotyped positions for defects. All the green units here are hexameres that have 6 neighbors, but a few of them have to be pentameres. And for a given template, right? For a given template, then the question is when and where will a growing lattice patch show a defect? So let's look at charges on topological disks. This is the simplest case you can imagine. It's just a flat patch of a perfect honeycomb lattice.
Can you take questions during the talk? Sorry, I'm new to this, Adil and Sascha. Hi, Rob.
Hi.
You know, you're probably going to get to this, but you raise or you beg an interesting question. Does the RNA actually encode for what you call the defects also? Is it a defect or is it actually extra coding? Does anybody know whether there's actually pentamer coding, or is it a feature or a defect?
I don't think anybody knows for sure. I mean, given that these have to assemble from monomers, you would think they will assemble into pentamers when they need to, right? Okay,
so it codes for the monomer, not for the hexamer. Okay, because you gave me an idea of a really cool toy at the viral scale. we need some good viral, some good recombinant DNA RNA people to work on it, but to make toys that are pentamer and heptamers also, and make all kinds of cool capsids.
Probably best to keep the questions at the end. We've got plenty of time for questions.
I will. I'm going to end it there. Sorry, that's it.
Okay. Right. So simple hexagonal patch, right? It's a topological disk. It has a boundary. So its Euler characteristic is 1. So Euler's theorem says you must have 6 defects. Well, where are the defects? It's just a flat patch of hexagon. Well, this is how you count. All the bulk hexagons have 6 neighbors and therefore have 0 topological charge. But the topological charge for boundary elements is different because it always depends on what you encounter as you take a circuit around the individual tile. So at the boundary, the topological charge is a difference to 4 neighbors, not to 6. The green guys all have 4 neighbors and have 0 topological charge, but there are the corners of the hexagon where you have topological charges of +1. So Euler's theorem is fulfilled, but it's fulfilled in a rather boring way. It's a flat patch. The boundary defects are defects, but they need no displacements from the regular positions. And in particular, if this is a mechanically active system, they will cost no mechanical energy because they are part of the regular grid. The same is true if you look at other shapes that are compatible with the planar topology. Here is a Drosophila eye that we analyzed by number of neighbors. All its bulk ommatidia, all its bulk facets have 6 neighbors. no topological charges, there are varying numbers of neighbors around the perimeter, but if you add up all the neighbors of the, as it happens, 100 boundary ommatidia, you get to 394. If every one of them had 4 neighbors and therefore a 0 topological charge, you would have to count 400. What you're counting is exactly 6 fewer, and that is the number of topological charges that you have to have. Okay, how do you change that? Well, the elementary change would be to have one disclination in bulk, to have one topological charge in bulk instead of at the boundary. And one way of doing that is to realize this pentagonal structure on the right-hand side. And this is something that most of you will have seen, but if I stop sharing for the moment, then I can hopefully show you. And what I should also do is I should turn off my virtual background. All right, so here I've printed out my hexagon, and I've cut out a 60-degree angle, all right? Because if I then connect this, I will have exactly the type of coordination and the type of connection that I want for this single defect structure. But as you know, it's very hard to do this while keeping the thing planar. I mean, I certainly can't do it with a sheet of paper. If I had a very soft rubber sheet, maybe I could do it. But you all know what happens if I actually connect the edges here. I'm making a cone. Right? I'm making a cone. This is now 5 defects at the boundary and 1 defect at the center, but it has buckled into a cone. In other words, I have paid for this defect because I wanted to avoid the large elastic strain that I would need to keep this structure planar while imposing this topology. So instead of keeping it planar, you pay for it by introducing Gaussian curvature. And it's a singular Gaussian curvature at the apex of the cone that relieves the strain from the singular disclination that sits at that same apex. But generally, of course, in a template situation where a cap is growing, the underlying template is not going to be a cone. It's going to be some shape that is given. And the question will then be, if and when is it going to be energetically favorable to have a disclination at the center of your cap versus keeping the cap defect-free? By the way, a shout out to Greg Grayson here for providing this nice algorithm or this nice Mathematica plugin to plot structures with and without defects. So that's going to be our elementary problem. Compare the elastic energy of a defect-free cap with that of a single disclination cap while that cap is growing. What's that mechanical energy? Well, in principle, it is made of a background term that is the energy of the defect-free lattice. That is not going to matter because it's a constant. Then you have energies associated with the defect cores, with the details of what's happening in the cores of the defects. We will assume that these energies are large. If they're not, you get a lot of dislocations, and that does not seem appropriate for many of the cases that I showed you, in particular not the virus capsids, but also not in many of the arthropod eyes. What that means then is if the core energy is large, you cannot just create pairs of defects all the time because it would cost you a lot. You cannot create pairs of positive, negative disclinations all the time, and you're restricted to having the minimum number of defects, number of cores, that is 6, according to Euler's theorem. And then this term is also constant. And so the only thing we need to figure out is the interaction energy of surface and defects. There is a well-developed formalism of that, which I will not go into the detail of, but I point you to these extremely impressive papers that go back to David Nelson and Mark Bowick and Alex Treviset and Luca Giomi, where roughly speaking, what's going on is this. You start with interacting entities on a lattice. Whatever your interaction is, you coarse grain it into a continuum limit that allows you to define displacements, uj, and strains, uij, and also to define continuum mechanical properties like Poisson's ratio and Young's modulus. And then you assume linear elasticity, or at least that's what also comes out of this limit to leading order, stress-strain relations. And every disclination then leads to a singular displacement field given by this term. And then you can derive a master equation for the Airy stress function that's related to the stress components. And that master equation has the character of a biharmonic, like anything that describes mechanics of curved elastic objects. And on the right-hand side, you have this eta of x, which is a combination of charges, if you will, of sources for stress, one of which is the singular term from the disclination, and the other is simply the Gaussian curvature. And you can see the minus sign between them. They're trying to compensate for each other. And unsurprisingly, the result formally, the elastic energy that follows from that formally is an integral over a Green's function of a biharmonic operator. That by itself is not terribly useful. It's very involved. It gets easier if you assume that the boundaries are stress-free, which again is not a bad assumption for many of these systems. Then things simplify significantly, and the elastic energy is an integral over a square of a quantity gamma, which turns out to be the trace of the stress tensor. And this quantity gamma itself fulfills a Poisson equation, which looks a lot more friendly now. I should note that all the operators here are covariant. So the Laplace operator is a Laplace-Beltrami operator. And so you're using the proper metric of everything. Before we go into how that is evaluated, let's talk about what we should expect. And expect, again, for the simplest case, where we're using a surface of revolution for our cap, given by a function f of r that is rotated around the axis of symmetry. Knowing f of r means we know things like the metric, we know things like the Gaussian curvature, and so on. And what we should expect is that as we increase the radius rb, the size, the boundary size of our surface of revolution, we should at first see, for a small cap that is nearly flat, that the favored structure has no defects. And then as you increase rb, at some point you should expect a transition to a single defect at the center being favorable. And you can compute these energies rigorously within this covariant formalism. And what we're after is the difference of elastic energies between the configuration where the defect is at the center and the configuration where the defect is at the boundary. When I say the defect, of course, there are still 5 defects at the boundary that are still not contributing to the energy. And it's just one of those defects that I'm ferrying between the boundary and the center. It turns out that this gamma, if you solve this Poisson equation, is made of 4 different parts. I'm not going to belabor their functional forms. One of them has an interesting logarithmic, or 2 of them have interesting singularities. I'm pointing out that one thing that you need to know for these quantities is this conformal radius, rho of r, which again follows directly from the shape f of r of the surface. This rho is going to become important. But so everything is known, everything can be computed, at least numerically. Now, here's a result for a shape family. We are keen on describing the transition here for a whole bunch of shapes simultaneously and ultimately for any shape. So what we're doing is we're choosing an f of r that we're rotating that looks like this. And it turns out these are spheroids. And kappa, which is the curvature at the apex, the curvature at r is 0, then encodes for what kind of spheroid we're looking at. Kappa is 1 is the sphere, less than 1 are oblate spheroids, greater than 1 are prolate spheroids. And what you see here as gray dots are the results of just evaluating the integral that I showed you before. So there is a transition between structures that have no defects and structures that have a single defect, being energetically favorable as you cross this threshold. This by itself is not terribly instructive. It doesn't give you a physical feel for why the transition happens where it happens, why it happens at this particular extent of the cap as you grow the cap from here to there. And there have been many attempts to formulate simple physical criteria. The simplest would be to make the same argument that I made for the cone. Maybe it's about local Gaussian curvature. Maybe the defect wants to sit where the Gaussian curvature is maximal. You can forget about that right away because oblate spheroids do show this transition to a defect at the center, but for oblate spheroids, the center has minimal Gaussian curvature, not maximal Gaussian curvature. Analytical attempts have focused so far on what is known as the small slope approximation, where you are simply Taylor expanding the shape such that you assume small radii and even the boundary radius RB is small in a certain sense. Then you approximate, for instance, this quantity gamma s that you need to evaluate gamma as a quadratic function. And these are also leading order terms in a small slope approximation. And then the integrals in our free energy difference become analytically tractable. And there's an explicit prediction then for the boundary. And the prediction for the boundary is equivalent to saying that this quantity, which is within the small slope approximation, a version of integral Gaussian curvature, is a constant, namely 2. If you compare that to the direct numerics, it does very well for large kappa, but for small kappa, it significantly deviates, and it doesn't even predict any transition for a significant chunk of the oblate spheroids. So this is out. Now, integral Gaussian curvature is a very attractive notion. It's a dimensionless quantity intrinsically, and it's a quantity that takes into account properties of the entire surface. Maybe it's just a small slope approximation. Maybe we should just evaluate the integral Gaussian curvature directly, which we can pretty easily once f of r is known. And this is a suggestion that many different people have made. Paul Chaikin's group, when they were conducting experiments of colloidal crystal caps and a couple of different theoretical approaches, the suggestion of what the constant integral Gaussian curvature should be varied, and depending on what kind of shape people were looking at. And if we try our best here to evaluate the integral Gaussian curvature and set it equal to a constant that matches the large kappa asymptote again, you can see that it's also not very good, and it deviates into the other direction from the rigorous covariant results. So that's also out. So we thought about how can we get a better physical criterion, a better simple criterion that gives us physical insight. And we quickly honed in on the quality of the small slope approximation. What you see here are different parts of this magical function gamma as a function of the radial coordinate, and the black ones are the full covariant expressions. The blue dotted thing here is gamma s as evaluated within the small slope approximation. And weirdly, you see that it does not even hit the correct value at 0, which is the expansion point of the small slope approximation. That's because gamma s is itself an integral quantity. I should say this is for a typical surface. For other surface shapes, this will look slightly different, but this discrepancy will actually remain. So our main goal was to improve on this approximation by making gamma s, by introducing a different gamma s approximation that is non-local. And that makes sure that not only is this gamma s 0 at 1, which it has to be, but that it also matches the value at 0 precisely. And otherwise, it is still a quadratic approximation. And the only thing that we're enforcing is the rigorous value of gamma s of 0, which is this integral here. That integral will become important, but for the moment, this is something that we can evaluate just by integration over a given shape. If you plug this into the full formula for delta f elastic, all the integrals become analytically tractable, and everything boils down to the following criterion. If RB becomes the critical value RC, so that delta FL is indeed 0, then this gamma S of naught has to be minus 1/6. And that's it. So the criterion is then that this quantity, which is the negative of that integral, must be 1/6. Let's evaluate that. It's just an integral of given quantities and find out for which r for given kappa, this integral becomes 1/6. And lo and behold, it goes through all the rigorously covariant points, whether they represent oblate or prolate shapes, all the way through. And you notice that this criterion uses neither local Gaussian curvature nor the full integral Gaussian curvature. It uses a certain version of weighted integral Gaussian curvature, and it's weighted with the logarithm of that conformal radius rho that I pointed out to you before. Now you'll say, okay, that was for spheroids. Maybe that's a particularly nice example. Here's a particularly non-nice example. This is a shape family of sort of sombrero-shaped surfaces given by this formula up here, and again parameterized by the central curvature kappa. And you can already see from the from the covariant points that the transition occurs much less uniformly. And if I try to employ a constant integral mean curvature, integral Gaussian curvature criterion, it fails spectacularly. It doesn't even have unique solutions. But if I employ the criterion of the weighted integral Gaussian curvature with this magic value of 1/6 for that integral, it still captures the entire behavior very nicely. And the same is true for all the shape families that we tried. Here's just a comparison of relative error by these other approaches versus this new approach of the weighted integral Gaussian curvature. And almost all these errors are below 1%, even for surfaces like these here, indicated by the plus and the cross, where we would not have expected it because they do not even have finite central curvature. We're not quite sure why it's so good even for shapes like that. All right. I will take the remaining minutes of my talk to talk a little bit about going beyond this very simple case that we looked at, this case of a rotationally symmetric cap, where we're just comparing the energies of all defects being at the boundary and one disclination being at the center. How do you know there are not intermediate defect positions? As you increase curvature, as you increase the extent of your cap, you might see that you go from being defect-free to having a defect at the center through intermediate defect positions, sort of a continuous way. Or you could find that you abruptly, in a discontinuous way, move from from the boundary to the central position. You can generalize the formalism that I showed you to accommodate intermediate radial positions. We are still on a rotationally symmetric cap, but now we allow for arbitrary radial positions of the defect. Everything gets a little more complicated, but again, everything is given by the shape of the surface. And so I can now evaluate the difference to the energy at the boundary for any defect position between R is 0 and R is RB. And that gives me sort of an energy landscape that I will normalize by a characteristic global curvature energy that's just given by this expression here. Here's an example. This is the sphere, the spheroid with kappa is 1. This is the energy difference as a function of defect position. And the red curve indicates the case that we have identified as the transition case. That's the critical RB is equal to RC, where the central energy is equal to the boundary energy. And as you can see, that energy landscape has a minimum. There is a position in between where the energy is even lower. And this is the position where you should expect the defect to sit. It's an intermediate position. And as you increase the extent of the cap, what you're doing is you're moving smoothly the equilibrium defect position from the boundary to this position and then further. And it's only when you reach this RC naught extent of the cap that you have actually settled your defect at the central position. By contrast, if I go to a prolate spheroid like kappa is 5, it's the other way around. Here is the energy landscape at transition, and it has a maximum. It has a hump. That's an energy barrier that has to be overcome. If I start at a smaller radius, like the blue curve, and my defect sits at the boundary, it will not move when I reach RC. It will only move when I reach this other radius RC1, because then energy is being smoothly minimized by placing the defect at the center. This kind of transition preserves symmetry because the only possible configurations are symmetric with respect to defect placement. The continuous transition here breaks the symmetry of the system. And so that's an important morphological difference, if you will. Quantitatively, that difference isn't that great when plotted in the transition diagram that you're now familiar with, the RB versus kappa diagram here for the spheroids. That tells you that the red line is our nominal transition from no defect to one defect at the center. But this red line is now flanked by these two orange and blue lines that tell you the range of RBs over which this transition happens, and whose order tells you whether the transition is continuous or discontinuous. And in this case, there is a higher order transition point, some critical kappa H on the order of 1. For lower kappas, you have continuous transition. For higher kappas, you have discontinuous transition. And again, the question is, beyond integrating these things out, these covariant integrals, can we get an analytical understanding? And here's what you can see. So different shape families show different transition energy landscapes. This is what I just showed you in principle. It's the spheroidal shape family. As kappa increases, you go from continuous to discontinuous at around a value of kappa is a little more than 1. Here's another shape family that doesn't look that different, just has a 3/2 power here instead of a 1/2 power. It's kind of bell-shaped. It has regions of negative Gaussian curvature. But as you can see, it does not show a transition. No matter what my kappa value is, you always have an energy hump. You always have an energy barrier. And if you introduce another parameter, and make a quartic surface where you change the prefactor of the fourth order and leave the prefactor of the second order, the central curvature, constant, you can see that this fourth order parameter can induce a transition as it increases from, again, continuous to discontinuous. And one thing that you notice right away empirically is that for the large kappa limit, or for the case of lambda is 0 for the quartic surface, the energy scales of these humps, of these barriers, are very closely the same. There's a universal energy scale here. Okay. It turns out in order to explain that analytically, and I'll be very brief in wrapping this up, that in order to analytically explain that, the non-local model that I presented to you is not enough. You have to go sort of one order higher. Instead of expanding the gamma S non-local such that you have a quadratic term, you want a fourth order term as well. That's not particularly onerous. All you need to introduce is gamma S double prime of 0, which turns out to be just kappa squared over 2. But the fourth order allows you to take into account and model things like what's happening with this quartic surface. You kind of know that you have to be able to evaluate a finite fourth derivative. The integrals then in the delta FL evaluation still are analytically tractable. And so this is sort of our analytical expression for the for this energy landscape at a given RD and RB. And if you expand everything in large kappa, this yields a pretty simple result. And if you evaluate numerically what all these pi over 864 are and so on, you find that this secondary elastic energy scale, which is either the depth of the minimum or the height of the maximum of the energy landscape at critical, normalized by this FB energy, is this combination of a constant minus another constant times lambda over kappa to the third. Again, lambda being the fourth derivative at the apex, kappa being the second derivative at the apex. And what does that tell us for our transition energy landscapes? Well, first of all,
will you be able to wrap up soon, Sascha? I think we'll probably have lots of questions already piling up.
This is literally my last slide here. Okay. You can see right away that if you take the large kappa limit or the lambda 0 limit, you have a constant left. So that explains the universal secondary energy scale that we observed here. It doesn't explain it particularly well quantitatively, but it's definitely in the right ballpark of a few percent of this FB energy scale, which also explains why the transition zone in the transition diagram is really rather narrow. If we look first now to the quartic surface, it's very natural that as you increase lambda, you induce a transition, because as you increase lambda at fixed kappa, you will have a sign change of the secondary energy scale. If we look at the bell-shaped example at the center, given this f of r, there is a relation between kappa and lambda, the second and fourth derivatives. Turns out to be lambda is equal to minus 3 kappa. Therefore, this term is always positive. This delta FL secondary is always positive. There can be no transition. And for the case of spheroids, with this f of r, turns out lambda is plus 3 kappa. And therefore, as you change kappa, you can indeed observe a transition from positive to negative delta FL secondary at around kappa is 1. So in conclusion, we're reconciling here the frustration between having topological constraints on curved surfaces and the need of finding a mechanical equilibrium, a minimum of mechanical energy. The limits of defect-free cap surfaces, that is the transition to this first disclination, are understood here via a simple criterion that is very accurate and can be universally applied to any given shape, and turns out to be a weighted integral Gaussian curvature. A higher order theory captures criteria for breaking the rotational symmetry, namely by describing whether transitions are continuous or discontinuous, second order or first order, if you will, and identifies universal properties of how this transition happens. And all this suggests that we can learn more about the engineering of defect placement through geometric control of these morphologies. Wouldn't it be nice if we could control if and when these defects insert into virus capsids that are growing? There's a few frontiers down here that maybe we can talk a bit more about. These are still very, very simple elementary cases. Things become much more involved when you try to deal with non-circular boundaries, when you deal with stress boundary conditions that are not no stress, and when you allow finite core energy and the interference of dislocations on top of the disclinations. But for now, thank you for your attention, and I'm happy to take your questions.